myself. I'm a senior security architect at Harvard. My background is offensive security engineering, offensive operation in general, and vulnerability research. Currently doing like R&D at Harvard, like a little bit far from smart contracts, but I like anything related to security in general. Planning stuff. There's my Twitter handle. A lot of shit posts like. Anyway, about me and about Harvard, like quickly, like with R&D work, I do like to do like UTXO-based research. I have found like multiple critical vulnerabilities in multiple UTX network, and that one is a screenshot. One of the like recently disclosed one was quite critical because you can shut down the entire network. There's other vulnerabilities like related to wallets. And if you have been in DSS in Paris, you would recognize me. I was talking about custody solutions or digital asset security. That's also one of my focus area. So one of our clients. So today's agenda is gonna talk about this research motivation and breaking down the EVM pipe codes and like overview really quick. Then talk about EVM control graph and building kind of function signatures that we can use these signatures later on to kind of search for similar bugs on chain directly. So it's kind of similar to the previous talk, but this one is like personal research, like how to do it, like get it real quick. I'm learning real quick. So the motivation is like back to 2017, I was like, okay, there's like Microsoft Patch Tuesday, there's a lot of vulnerabilities coming out in Web 2, and I was like, okay, I want just to have like visibility. And yes, there is also like Internet Search Engine, but I don't have they have this capability of touching the entire IPv 4 stack within hours. So I was like, okay, I'm gonna build something like this in-house, and I did. It's working till today. So the idea was like, okay, why I don't do this on-chain? So I can, whenever like there's a vulnerability getting disclosed or an interesting logical vulnerability coming up, I can identify several variants of this bug or this vulnerability on other contracts. So there's like few problems and challenges. For example, downloading the bytecodes, generating the control flow graph of the bytecode, and the compiler optimization on name versions, because for example, different compiler versions is kind of producing almost completely, not completely different, but different bytecode. So I needed to solve this problem. So downloading the bytecodes, there's two ways to approach it. Like you can use the Ethereum ETL. It's quite slow, a little bit expensive if you gotta buy like RPC provider and stuff like that. So. And definitely slow, and it's one thing unless you like run cron jobs or stuff like that, and also you need to parse the data coming out from this one. Second solution is like just getting into the EVM node and search for a similar function and just write like hook it up and write this code into desk or database or whatever you're gonna interact with this bytecodes later on. This is fast, but requires you to like to mess with like the EVM and the node, and also definitely run a full node on a local server or whatever. So bytecode overview, like I think most of you are familiar with this. Like you have the constructor code, you have the runtime, you have the metadata. The metadata does not always exist. The constructor code ends always with a stop token. Ends with like stop tokens like reverse, stop, or return. But most of the cases we want to stop at the actual return instruction. There could be like multiple return instructions within one instructor, but definitely you don't want to use like a stop token as like stop or revert, because it means there's something already went wrong with the constructor, so it doesn't make sense. So the actual thing we're gonna look at is the runtime code, which contains like the main implementation of the contract and the dispatcher function or the main function. We're gonna talk about this later on. So within the runtime, we have like multiple tasks. We need to find the function dispatcher, extract like signature and offset, and identify like basic code blocks or CFGs or all of the edges, because we're gonna use them later on. So as you see right here, that's kind of I would say dispatching basic block. So you have like the function signature, and you do have like the offset, like whatever this function signature getting matched, you're gonna jump to this particular offset. So the dispatcher block is kind of most of like compilers and other stuff, like they're just push the signatures and compare it and just conditional jump to the particular offset. So we do have a problem with that because when we are parsing or extracting the functions within the contract, there's already like getter functions. Like for example, the function like does not take any kind of input, but just return specific values within the contract. We are definitely not interested in this kind of function, so we're technically excluding them. And this function can be identified from earliest code blocks after the first jump, technically, because you might see kind of validation on the call value, like, okay, did the user call this function with argument or not, and stuff like that. So wherever you see, there's also other methods we can discuss about them outside because of the time, where you can identify whatever it's like getter function or an functions that actually has something to do with the contract. So yeah, we did the functions, and we will start to grab all the basic blocks, ongoing basic blocks, or call like all outgoing blocks, basic blocks from like EVM CGP Builder. I'm using this Python library to generate the kind of like code basic blocks. It's not that much effective. It's producing, I would say, like at the final version of this product or this tool, it's producing like false positive, but say still like this is an idea, and if you would like to implement something better, this is in-house tool I developed for myself just for fun. So you can definitely do much better. So you identify like all outgoing code blocks, and there's a set of rules to exclude like a default checks. Like for example, if you are calling a getter function, there will be like kind of a check on the actual like call value and stuff like that. So there's similar rules just to filter out like unnecessary code blocks, and then you will have a specific code blocks like as you see in the photo, like when you match with the actual offset or you go within the conditional jump, you land into like kind of a flow of the code, like where all of them are going to be related to the specific function. So putting all together, we have now like function signature, we have outgoing code, the code blocks, all of them. I mean the necessary one only, and we do have like definitely all the function-related code blocks, and we do have the compiler name and version from the metadata. So I think this is time to do like some art. So what's next? We need like storage. We need to store this information somewhere, and a database technically, or an indexing engine like Elasticsearch. Then later on you can just find similar or queries that database to find similar variants of this particular bug. And definitely you need like query mechanism, and you need like technically to hash everything. So I will start from hashing everything. So we have like the function body signature, which is like only the necessary code blocks we have after like the offset jump, after stripping out all the default checks and other stuff, and then we're gonna like hash it with the compiler version. So technically, it will identify all kind of the code that we will have copy and paste, because we are Web3 and we are like in general, like people are just copying paste code from everywhere, like from AI, definitely for Stack Overflow, like old school people, like GitHub open source projects and stuff like that. So definitely like there's copy paste and there's copy paste code over chains, and yeah, the results was like really massive after doing that. And the query mechanism is like function matching, excluding the unsupported compilers and uncommon. Like for example, this entire operation is like about building this as like big scale. So we are not really going to take few samples of the bytecodes deployed over multiple networks and we're gonna say, okay, this is how it works here. So, and we're gonna write a rule based on that. So it's more like you are doing kind of data analytics on the bytecode, like the massive bytecodes you have, because yeah, also this, like side note, this is consuming too much storage, because around 500 gigabytes from parsed bytecodes, but multiple chains definitely. So on the Elastic instance I have, so yeah, that's definitely massive. So you need kind of to consider when you're writing rules regarding the actual signatures you gotta pass, or whenever you kind of refactor a specific function to exclude like common checks and stuff like that. So we store the hashes. We do have like, okay, we know that this specific implementation was this specific compiler version producing this specific hash, so we can search for this hash and we will find just similar implementation across multiple chains. But also, if people, like for example, they just could rename the function, so we still will be able to find this function, because we already have like the actual function body implementation and its hashes. So why we need all of that? We need all of that like for a secure chain. Like we need to have like secure chains. We need to unify like different bug variants. And yeah, definitely the number is quite high because of I did not filter about, for example, people just deploying contracts just for education purposes, like for testing purposes. Like really done with contracts. So they're on the chain. And for me right now, I don't have like an actual way to do that. There's an actual way, definitely, but it's gonna be like, it's gonna impact the performance and the speed of the entire tool. So in terms of like parsing the bytecode. So I didn't go with that, so I just put everything in. And yeah, we unify like variants. For example, let's say that you have found during like an audit or whatever, you found like a really interesting logical vulnerability and you would like to unify similar contracts that has the same issue. You can just go with that approach and that's it, you'll find. And static analyzers are sucks, because before I do that, I have tried something like just pulling all down like GitHub repos and public repos. I did this like 3 years ago, or a few years ago, I don't remember the exact number, and I tried to run like some static analyzer and all parse the results, store them in the database, but that was like full of false positive. Even they were missing stuff, because, for example, this photo, like, okay, there's no self-destruct anymore, but here's like, because this is like from an old presentation photo, but the static tool analyzer, like, regardless how much call detectors you have, you might definitely miss some bugs. I mean, if static analyzer can detect all the bugs, we wouldn't need auditors like so far. So people can just write detectors and run them and go, and that's it. So, yep, that's all. That's something in Turkish says like, have a good day, and stuff like that. Okay, thank you very much.